Hello, everyone. Thank you so much for joining us today at the OCP 2020 Virtual Summit. My name is Caleb Lusk with Rittal, and alongside me is Brian Kincaid with Nye Lubricants. Our project that we are presenting today is focused on the BusBar plating and connection reliability. We initiated this project to better understand the plating thickness on the BusBar and the benefits of lubricant on the connections. In other words, we wanted to ask the following questions. Are equipment connections good today? Could connections today be better tomorrow? Is BusBar plating sufficient today? Is there an opportunity where the plating thickness could be reduced? As we step through our presentation, we hope to answer these questions for you. At the end of our project, we plan to submit this study and our test results as a white paper to the community. During this project, insertion force, insertion wear, transportation, and fretting corrosion were all tested. After reviewing our test plans, we decided to break this into 3 phases. Phase 1, with the BusBar from today's production, we tested insertion force, insertion wear, fretting corrosion, and the impact from transportation. We'll get into a little more details later on about this. Phase 2, we wanted to share the results with the community for comments and feedback. And then finally, phase 3, if the test results from phase 1 point toward benefits of less plating and added benefits of lubricant, we'll consider doing additional testing with reduced silver plating. Before we get into the project detail, we wanted to thank those who willingly participated by supplying samples or did testing, supplied the test facilities. So the rack was provided by Rittal, and the transportation testing was provided by Rittal. The connectors were supplied by Amphenol, 2CRSI, and TE. And Nye Lubricants supplied the grease samples and performed the fretting and insertion testing. Now I'm going to hand it over to Brian, and he can talk about some of his test results.
Here we want to explain to everybody exactly what fretting corrosion is. A lot of people understand that an electrical connection is made at the peaks of the contact surfaces or the asperities of the contact surfaces, as we show in the left-hand illustration. But a lot of people don't understand about fretting, where actually micromotion creates debris and oxidation, and then that oxidation builds up and separates the contact, separates the surfaces so the peaks can't meet. And so that's where you get an open connection. So where can this micromotion occur? You can see it, you can see contact wear for mating cycles, right? You kind of expect that. But micromotion occurs with a very little bit of movement across the contact surface, and that can occur during transport. It can occur during temperature expansion and contraction if the materials are moving at different, expanding at different coefficients of expansion. And it can also see transmitted mechanical vibration from fans and blowers. So what we wanted to do was look at, one of the first tests we wanted to do was look at insertion force. This is just trying to see what does it take to put a rack in, what's the force that happens, does the lubrication improve the insertion force for the silver on silver BusBar clips. So we looked at a TE connector unlubricated, an Amphenol proprietary lubricated connector, 2CRSI lubricated connector using, it was basically lubricated with Amphenol's proprietary materials. And then we lubricated the TE with 3 of our different greases. And we use a standard technique, standard piece of equipment, the Instron 5566.
I do want to mention one thing here, that we made this test rigid for insertion, basically without the float that's in the design. This way it can produce true results of the lubricants being added.
Good point. So what we ended up finding when we went through everything was that the 769G and the 8132 lubricated connectors showed a improvement over TE dry that was significant, and improvement over the 2CRSI that was significant, and an improvement over the Amphenol that was significant. So that's what we would expect, and we can share with people the additional details behind that. But it wasn't anything, shouldn't be a big surprise. When you add grease to a connector, the insertion force goes down. The next set of tests that we wanted to do was insertion cycle wear tests. And in this testing, we wanted to see what happened to the contact resistance over the insertions, as well as what happened to the scar depth at the end. And we initially started with wanting to do 100 insertions and look at the change. And we inserted in the middle, after talking to the community, a temperature bake of 85°C for 7 days. So what we have is a lot of different contact resistance measurements throughout the test procedure, and then the scar depth analysis at the end. So what we found out after looking at everything, so a lot of people think that connectors will cause a problem with contact resistance, is that really that wasn't the case. And in the case of the lowest row here, TE with the 769G lubricant, it had the most consistent measurement of contact resistance throughout the whole cycle. But all in all, everything was all in range for everybody. But you could see a little bit of a consistency with 769G. So that sort of became what I think is my favorite grease for this application right now. Next, though, we looked at the insertion cycle wear scar depth, and there things get really interesting. First of all, the TE had a high insertion force that made it so that we could only do 50 insertions. And so that's the first column. And so what we have here is, you see the number of insertions, our scar depth measurement, a visual picture of the connection, that the contact that we were measuring, the scars that we are measuring, and a surface profile scan that we did. So as you run through this, you will see that that basically the lubricant reduced the scar depth significantly. And then the other thing that you can look at, if you compare TE to 2CRSI and the Amphenol scars, is that the actual scar shape and length is different because of the different contact profile that each of the connectors have. So even though we use the same BusBar, we had different scars on it because of how they contacted the BusBar. So what we ended up doing, just to sort of make it a little bit more obvious, is I just put in just what it looks like for the worst and best case situations. And so what you see is that TE dry, after 50 insertions, there was material buildup at the end of the scars, and you see the scar depth. And then for the T769 lubricated with 769G at 100 insertions, you see the average scar depth, and you can see how much less it impacted the surface of the metal. So what I want to do is turn it over to Caleb to talk about the setup for the rack transport wear test.
Yeah, thanks, Brian. That's really good detail there. And yeah, to run through transportation testing that was performed, we basically had 2 racks were built with dry and lubricated connections. Each rack was loaded to max capacity per the spec of 1,400 kilograms. And our test schedule followed the ASTM D4169 protocol for transportation. We cycled 3 times at 40 minutes on the low level, the 15 minutes on medium level, and then 5 minutes on high level. We performed drop testing for impact, and the rack sustained 4 edge drops, 4 rotational edge drops, and a single flat drop. And then from there, we scar depth measurements were taken. From these photos, they're just simply showing the lubricant applied to the connectors. And for reference, we wanted to include the ASTM spec used in the transportation testing. So this illustration is showing the definition of the drops. Starting from the left, the edge is on the floor, and the opposite edge is raised 6 inches and then released. The rotational edge drop in the middle picture there is 4 inches on the support height and then drops 6 inches on the other edge. And the flat drop, which is 6 inches directly off of the floor, dropping straight onto the floor. So then here again, just a few pictures from the testing that was done. And a side note, I did not attach any pictures of our shake and vibe. They tend to be a little blurry, so they are not included in our pictures here. From a visible standpoint, the transportation testing looks less severe compared to our Instron insertion test. On the left here, you can see the scarring from rack B. Compared to the right side is a picture from the machine insertion test. The scar profile analysis tells the story, though.
Yeah, so that was what was interesting to me, because I actually thought that the rack transport test really wasn't that much, wasn't really that bad, and that the insertion wear was really the problem. But when we looked at the TE dry results that we had from the wear testing, and we looked at what we thought visually was the worst TE dry, you can see that it was kind of similar to 50 insertions. And when we looked at Amphenol, which was the other connector that we had in the rack transport testing, you could see also that the Amphenol scar was about equivalent to 50 insertions. So, we can't quite draw that conclusion because there was different bus bars manufacturers used in each test. But what we're going through right now is some additional insertion wear testing to confirm that the scars that we see in the wear testing, if they're similar, then that sort of assumption holds true that the rack transport is equivalent to about 50 insertions. So from our point of view, we saw this as, what's the definition of the problem? How deep does the scar get? And can we use insertion wear testing going forward to sort of characterize what happens in rack transport tests? Because it's much easier to do the insertion wear testing than to do the rack transport.
Yeah, exactly. Yeah, so that is
build a test, right?
Much easier. Yeah, what can you tell us about the fretting life cycle?
So the fretting life cycle test is something that we do, and we've been doing in the automotive industry. And what we wanted to do was, the first set was to do an unlubricated connection for the first test, because that's usually the fastest. And what we would do is we cycle at 10 hertz and 40 micron displacement, and watch the contact resistance. We're looking for the contact resistance to rise, because that's what shows us that the fretting corrosion has occurred, that we're seeing that oxidation. And so that sets up the sort of unlubricated lifetime cycles. And that allows us to then do lubricated connections and just look at what happens over that sort of short cycle. What we think is the fastest would be the dry testing. So it gives us the most amount of information soon, rather than trying to do lubricated to failure, which could go 10 or 20 times longer. So in doing that, though, we started with TE dry, and it's been going much longer than 8 million cycles. Matter of fact, it's probably at 15 or 20 million now. We'll have an update, when we do we'll probably have some results when we do the paper, and we'll be moving on to trying to get some other connectors under the test. But because we believe, because of the thick silver, the 11 micron plating thickness of silver, that the fretting dry life cycle test is going to take a long time to get all the results. So stay tuned.
Yeah, it's definitely interesting from everything that we've done so far and the results that have come in. Like you said, it's good detail, and we're looking forward to the end results of what we come up with here. So yeah, so wrapping up and looking at our next steps, we plan to finish phase 1 around June timeframe, with phase 2 probably around July, and phase 3 will move more towards the 4th quarter of this year, and where we're going to submit our white paper. So just to a little company overview here. Rittal is a global leader in the data center solutions arena, providing everything from rack infrastructure and monitoring to high density cooling and data center container platforms.
And Nye, well, we've been around making specialty lubricants for a lot of different applications, but what's related to this presentation is that we've been addressing connector reliability with automotive OEMs for more than 30 years, and have been helping server OEMs with similar types of problems, but based on tin-plated BusBar connections.
So for our call to action, participation is definitely welcomed. You can get involved by just joining the Rack and Power calls. White paper submission, again, is planned to be completed this year, and you can find out more with the links below. My email address and Brian's email is down below, as well as the mailing list there. So again, thanks to everyone for attending. If there are any questions, please feel free to get in contact with Brian or myself. We'll be happy to share what we've learned so far.
All right, so we have some questions, Caleb.
Yeah, thanks everybody. Everybody that has jumped into the meeting, and appreciate everybody hanging out with us today and watching the testing that we've done so far. So, okay, let's see. We'll switch back and forth between chat and Q&A because I know they kind of come into both.
So we have one set of questions around
NS referred in the contact resistance table.
Yeah, and it kind of relates to why did we stop testing after 50 cycles. So the insertion force was crazy for us, crazy high, and the person that was doing it for the TE one, we had it basically done mechanically with a motor, but the insertion force was so high for the TE drive that he was doing it by hand, and it got even worse for after the bake out. So he stopped doing it. He was like, whatever, he was having so much of a hard time doing the insertion that he stopped doing it. So that's why we stopped at 50 cycles. So it was a very interesting thing. We can certainly in our paper we'll have some more details about it. We wanted to keep it at a high level for this presentation, but that's what happened. It became almost physically impossible to insert it on the BusBar, which was strange to us, but that's what happened.
Good question.
And so then we had
Mike,
contact.
Sorry.
Go ahead.
Yeah, so Mike, you had a question. What was the underplating and thickness of both the BusBar and the connectors? So we used the 12-volt V2 BusBar from production today, and that is copper with nickel plating. I want to say 5 to 7 microns, and over top of that is silver, which is 11. It's 11 microns. I think it goes up to 14 is the range. So hopefully that answers that question, Mike. Another one. It appears that the testing was performed on 12-volt setup. If this is the case, do you expect similar results for a 48-volt setup? Yeah, that's a good question. So we wanted to draw a baseline from the testing that we've done so far, and eventually be able to take this into not only 48-volt V2, but I know that's a small arena, but we wanted to be able to look at this and kind of tee it up for V3 as well. So yeah, the jury's out on whether we would expect similar results just because of the way the clip is designed for 48, right, versus 12. But generally speaking, I would expect to see the same results with the application of lubricant, where it reduces, the frictional force for sure.
Exactly. Would reduce
Brian,
the insertion. Yeah, it would reduce the insertion and the wear. I do think the contact, the mechanics of the contact could be different enough that it should get the probably the 50 to 100 insertion wear testing done at least. And if we thought it was, we wanted to, it might be worth doing some kind of transport test. But if we can, like where we're at right now, we're feeling like the insertion wear and the 100 insertion wear testing seems to be pretty indicative of what's going to happen. So if we feel comfortable with that, I'd go with that, because you can do 100 insertions pretty fast, and you don't need 3 racks of equipment either, or 2 racks of equipment. So
right.
I'd probably go in that direction at least to get a good feeling for it. And then we had a question about if lubrication is advised, how do you think it can be applied in the data center at the IT provider level? And how long will be the reapplying interval? So first, the rack's already been transported and it's at the data center. So it saw the transport wear. So there is one scar there, right, from the drop. The drop made one scar. So maybe real life will make something different, but there'll be some wear from the transport. If you apply the grease, it shouldn't need to be reapplied. It should be pretty much a one-time application. Would I reapply it if I put another server in at a later time? Yeah, I would probably put it on the clip. And I think, we can't go back, but in the picture, I think there was a shot of where how the grease was applied, and it went through the basically a bead at the leading edge of the clip is how it was applied to the server.
Right, and
So,
it's a good question too because of how whether in the DC or at the integrator basically.
Yeah.
And like Brian said, that's the reason we set our test method up the way we did. We wanted to look at every influence on the connection, not just in operation, but as well as the transportation. So, good question.
Yeah. And what got me interested in the silver side was we saw this type of problem in tin-plated connections for bus bars, which is sort of the version 1 and old school stuff that's used in a lot of data centers today. And there, the server OEMs were seeing problems, and it was related to having shipped a rack on either a long distance or bad roads for a long distance. And they could kind of see the difference in in the failure rates in the field accordingly to how bad the transport was. So that's what got me into participating in the OCP rack and power group.
See if we have any other questions here that have come in. Maybe one from Mark.
Yeah.
Yeah, go ahead.
Yeah, so the question was if there was any SEM done. We didn't. I don't think we saw base metal exposed. There was some thought of... Go ahead.
I was just going to say the base metal we did. If I remember right, so far we didn't go through down to copper. We went
Correct.
through silver plating, obviously, and definitely with the lubricants, we hardly touched the, ate into the silver, but no base material was exposed.
Yeah, yeah.
That's an important area too to kind of pick up on as well. The base material of silver being at 11 microns, with and without lubricant, again, if I remember our data sets correctly, we didn't necessarily go into all of the available silver that's there as well. So
right.
There potentially could be room, like we said, started out in the presentation saying, can it be optimized? How are the connections today? Can we improve them tomorrow? And the data and the testing is leaning towards yes, but Brian and I still have a lot of work to do. We're still testing multiple sets as we continue down this path. So, good questions. Any other questions that? Here's
so
another question.
Somebody asked about if our white paper will have the full data.
Yes. When we submit the white paper, we are planning to submit full data. I'm assuming full data, everything that we've done from testing, our validation, and all the data collected. We will plan to put that in the white paper.
Right, and the participants can see it now if they want.
Yes.
They've all the connector people have seen pieces of it.
Okay. It looks like the questions have slowed down. So if there are any other questions, there's still about a minute left to throw it in there. If not, feel free to reach out to Brian or myself. And our contact details are in there. Again, appreciate everybody stopping in.
Thank you.
And
Thank you
taking
so
the time.
Thanks, everyone.